In this video, I'll demonstrate how to use the permutation and combination formulas in Excel. In this dataset, we have the entire diamond inventory of a jeweler. If the jeweler wants to randomly select 4 diamonds to set up a display in the front window, the order of the diamonds selected will matter, because each permutation or arrangement of 4 diamonds will require a modification to the display. Assume that 4 of the diamonds will be selected at random. How many possible permutations of 4 randomly drawn diamonds are possible? If we solved it by hand, or rather by calculator, this is doable. We would use this formula and crunch through some factorials. No big deal. However, Excel will do the work for us with a formula called permute. Let's take a look at the formula. Equals permute, and when I click open parenthesis, I can then click the F sub x button and the dialog box will open. Number is the n I have right here, the number that's in inventory in this case, and R is the number chosen. How many of the inventory will I select? If there were only 4 diamonds, and all 4 would therefore have to be selected, but the order does matter, how many permutations of those 4 diamonds are there? The answer is 24. If I put 4 here, and 4 chosen, you can see the answer comes up already as 24. But we have 33 diamonds, so we would expect a much larger number of permutations. Let's see what happens. 982,000, almost 1,000,000 permutations. Of course, in the real world, it is more likely that the jeweler would not pick randomly, but this example does illustrate how many possible outcomes there are when the order matters. The combination formula, combin, looks very similar. Let's go ahead and open the dialog box, equals combin, open parenthesis, and then click the F sub x to see the dialog box. The difference is in the denominator in this formula. Because the denominator has an extra component, we can expect our result using the same numbers to be smaller. Let's check it with the example of 4 diamonds and all 4 being drawn. We use this formula when the order does not matter, only that we have 4. So if we have 4 in inventory and we're going to select 4 and the order doesn't matter, you can guess already that we should have 1 combination. Let's put that in here, 4 and 4. And as you can see, we have 1 possible combination. In this example, if we want to know how many combinations of 4 diamonds are possible, and we don't care about the ordering, only that a diamond has been selected, it turns out that there are about 41,000 combinations. The difference between permutations and combinations comes down to whether you care about how the items are ordered. If the order matters, then use the permutation formula. If the order doesn't matter, use the combination formula. This video demonstrated how to apply the principles of counting using the permute and combin formulas in Excel. In this video, I will demonstrate how to solve Bayes' theorem using a table format and using sum product. Bayes' theorem can be applied when we have 2 or more mutually exclusive and collectively exhaustive events for which the probability is known. That probability is revised given additional information. Bayes' theorem is a combined application of conditional and joint probability. The formula is as shown here. We will replace this formula with a table and solve for the posterior probability, that is, the probability given an intervening event. Here we have an example in which a police department has collected statistics about thefts from garages in an upper middle class neighborhood. 25% of residents leave their garage door unlocked when they leave home. That means 75% lock their garage. The police chief is making a presentation at an upcoming neighborhood watch meeting and wants to estimate the probability that a homeowner experiencing theft left the garage door open. You may be tempted to say 5%, but that's incorrect. A random homeowner may have left the garage door locked or unlocked. Given a garage door is unlocked, there is a 5% probability of theft. Given it is locked, the probability is 1%. These are conditional probabilities based on the event of locked or unlocked. Next, we have a joint probability. A garage is unlocked and a theft happens. The "and" tells us to multiply the two together. The same with the probability that a garage is locked and theft happens. In this cell, we're going to multiply the prior probability times the conditional probability. We have a joint probability that a garage door is left unlocked and it had a theft of 1.25%, and a 0.75% probability a garage door is locked and that there is a theft. We want to find the probability of the garage being unlocked given a theft, or the probability of the garage being locked given a theft. In other words, given that a theft occurs, was the garage unlocked or locked? Before we can do that, we need to total up our joint probability column, and a cool shortcut is Alt equals. It will sum up the cells above it. Now it's a simple relative probability equal this joint probability divided by the total of the column. And I'll use F4 to lock it. Once I've locked the cell, I can drag it down. These two numbers should add up to 1. I'll use my Alt equal shortcut, and they do add up to 100%. This is a tabular format for Bayes' theorem. Notice that when we calculated the joint probability, which is the denominator of our posterior probability formula, we have an application of sum product because we multiplied prior probability times conditional, prior probability times conditional, and added them together and got 0.02. We can therefore use a single cell to calculate the posterior probability that a garage door was left open given a theft. In the numerator, we will put this joint probability. That's what goes in the numerator here. F3 is the joint probability. In the denominator, we put the total of the joint probabilities equals the prior probability times the conditional probability divided by the sum product of this column and this column, which again is going to give me the total of joint probabilities, 0.625 or 62.5%. In this video, we have demonstrated how to set up Bayes' theorem using a table format and using sum product. In this video, I'll demonstrate how to build a discrete probability distribution from a frequency table. In this dataset, we have the results of a survey of 100 households in Boise, Idaho. These households shared how many HD TV devices are in use in each home. The value of the discrete random variable is in the first column. Households may have 0, 1, 2, 3, 4, or the largest number reported, 5 HD TVs. The next column counts the frequency of each value. The frequency column adds to 100. To convert this to a discrete probability distribution, I've added the relative frequency column, and we're going to calculate the probability of X. I'm going to lock this cell with F4 on my keyboard. Now that I've locked the cell, I can drag it down the column, and I see that it does add to 100%. Once we have the table completed, it's easy to add a graph of our probability distribution. I'm going to select my X and my relative frequency columns, and then I'm going to insert charts, all charts, and I'd like a column chart. This one here. I can change the title to be more descriptive. I might also like to do a little bit of modification for my graph design. I really don't need the y-axis. It's easier to put the labels right here on the graph, and there are a few options that will allow me to do that. I like this one. I'll go ahead and choose that design. I'm done with the graph. I've now graphed my probability distribution. Other information that may be useful to us is the mean of this probability distribution, the variance, and the standard deviation. The mean is the sum of x times the probability of x. It's similar to a weighted mean. And what I've just described is an application of the sum product formula. The two columns that we'll include in sum product are the value of x, not the frequency, but the actual value, the number of HDTVs per household, and the probability of x. We'll take this column and this column. The mean of the probability distribution given our data set is 2.27. The variance is the x column minus the mean we just calculated squared times the probability of x. I'll create a new column for x minus mu squared. I'm going to take equals x minus mu, put parentheses around it, and square the whole thing. So I'll use the upward caret 2. I'm going to lock that B12, the mu, and then I can drag it down the column. And I've now calculated this portion of the formula, the x minus mu squared. My formula is equals sum product, and then these two columns. The variance is 1.9571. The standard deviation is simply the square root of variance, square root of this. This video demonstrated how to build and graph a discrete probability distribution, and how to calculate the expected mean, variance, and standard deviation of that distribution.